For thousands of years, humanity has dreamed of building bigger, taller, and stronger structures. Ancient civilizations raised pyramids using little more than human strength, simple tools, and incredible determination. Massive stone blocks weighing several tons were transported across deserts, lifted into place without modern machinery, and assembled into monuments that still stand thousands of years later. Centuries afterward, engineers built cathedrals, castles, bridges, and canals using techniques that pushed the limits of their time. But as civilizations expanded and engineering ambitions grew, human labor alone was no longer enough. The Industrial Revolution changed everything. Steam engines replaced manual work, steel transformed construction, and machines began accomplishing tasks that would have required thousands of workers only decades earlier. That transformation marked the beginning of a new era, an era where engineering was no longer limited by human strength, but by the imagination of those designing the machines. Today, every modern megaproject begins with equipment that is almost impossible to comprehend. Before the first foundation is poured, before the first tunnel is excavated, and before the first skyscraper begins rising into the sky, gigantic construction machines arrive at the site. Some are taller than 20-story buildings. Others weigh more than naval warships. Many cost hundreds of millions of dollars and operate continuously for years without leaving the construction site. These machines are not simply tools. They are engineering masterpieces built to create other engineering masterpieces. Modern civilization depends on these giants more than most people realize. Every highway crossing a mountain range, every airport runway stretching across the horizon, every offshore wind farm, every hydroelectric dam, every underground metro system, and every futuristic city begins with machines capable of moving mountains, cutting through solid rock, lifting unimaginable loads, and working in environments too dangerous for human workers alone. Without them, many of the world's greatest infrastructure projects would remain nothing more than architectural drawings. One of the greatest challenges in modern construction is scale. Today's engineers no longer build only bridges spanning rivers or buildings reaching a few dozen floors. They construct airports covering hundreds of square kilometers, tunnels extending beneath oceans, dams capable of holding billions of cubic meters of water, and cities designed to house millions of people. Such projects require machines that can perform continuously under extreme conditions while maintaining extraordinary precision. A tiny positioning error during the installation of a bridge segment weighing thousands of tons could delay an entire project. A slight deviation during tunnel excavation could prevent two tunnel sections from connecting after years of construction. Precision has become just as important as power. Building these machines is often as impressive as the projects they eventually create. Engineers spend years designing equipment capable of surviving enormous mechanical loads, harsh weather, vibration, dust, heat, and continuous operation. Every hydraulic cylinder, steel component, electric motor, gearbox, and control system must work together perfectly because failure is rarely a simple inconvenience. When a machine weighing thousands of tons stops operating, entire construction projects can come to a standstill, costing millions of dollars every single day. Technology has transformed construction equipment just as dramatically as it has transformed airplanes or spacecraft. Modern machines use satellite positioning accurate to within centimeters, laser guidance systems, three-dimensional terrain mapping, artificial intelligence, remote diagnostics, autonomous operating modes, and sophisticated computer networks that monitor every moving component in real time. Operators sitting inside climate-controlled cabins often control machines larger than football stadiums using joysticks, touchscreens, and digital displays rather than mechanical levers. Behind every movement is an enormous amount of engineering designed to maximize productivity while protecting both workers and equipment. Yet despite their incredible size, these machines are only as effective as the engineers who design them and the operators who control them. Experience, planning, and precision remain essential. Every movement on a construction site must be carefully coordinated because dozens of giant machines often work together simultaneously. Excavators remove earth while bulldozers reshape the terrain. Cranes lift massive structural components into place while concrete pumps deliver thousands of cubic meters of concrete. Survey teams continuously verify accuracy while engineers monitor every stage of construction. It is a carefully choreographed operation where every machine performs a specific role in building something far greater than itself. Among all these engineering giants, however, a small group of machines stands above the rest. They are so enormous that photographs often fail to capture their true scale. Standing beside them, a person appears no larger than an ant. Some stretch hundreds of meters in length. Others move entire hillsides one bucket at a time. These are the largest construction machines ever built by humanity. And in the next chapter, we'll step inside these incredible mechanical giants to discover how they perform tasks that once seemed completely impossible. When people think of excavators, they usually imagine the machines seen on construction sites, digging foundations for houses or roads. But those machines are tiny compared to the true giants of the engineering world. Hidden inside massive open-pit mines are machines so enormous that they completely redefine the meaning of construction equipment. Some stand taller than 20-story buildings. Others stretch longer than 2 football fields. Weighing more than 14,000 tons, these engineering giants are among the largest land vehicles ever built by humanity. Their purpose is simple but extraordinary: to move mountains. Every day, they remove millions of tons of earth, exposing the valuable minerals buried deep beneath the surface that make modern civilization possible. Among them, one machine has become a true engineering legend: the Bagger 293. Built in Germany by TACREF, the Bagger 293 is one of the largest bucket wheel excavators ever constructed. Standing approximately 96 meters tall and extending more than 200 meters in length, it weighs around 14,000 tons. To put that into perspective, it is heavier than many naval destroyers and significantly taller than the Statue of Liberty. Yet, despite its incredible size, the machine moves continuously across mining sites, using enormous crawler tracks that distribute its weight across the ground. Without these specially designed tracks, the machine would immediately sink into the soft soil beneath it. At the front of the Bagger 293 sits its most recognizable feature: a gigantic rotating bucket wheel measuring more than 20 meters in diameter. Around its circumference are multiple massive buckets made from extremely durable steel. As the wheel slowly rotates, each bucket cuts into the earth, collecting soil, clay, sand, or lignite before dumping the material onto a series of conveyor belts running through the center of the machine. Unlike ordinary excavators that repeatedly dig and dump individual bucket loads, the Bagger 293 performs one continuous operation. Every second, the bucket wheel rotates while conveyor belts transport excavated material toward additional conveyor systems stretching for kilometers across the mining site. This continuous process allows the machine to move hundreds of thousands of cubic meters of material every single day. Powering such an enormous machine presents another remarkable engineering challenge. Contrary to what many people expect, machines of this size do not operate using conventional diesel engines alone. The Bagger 293 receives electricity directly from the power grid through gigantic high-voltage cables continuously connected to the machine as it moves. At full operation, its electrical consumption is enormous, supplying dozens of electric motors that drive the crawler tracks, conveyor belts, bucket wheel, hydraulic systems, cooling equipment, and sophisticated control systems. Every component must work in perfect synchronization because even a brief interruption can affect production across the entire mining operation. Another legendary machine is the Bagger 288. Built several years before the Bagger 293, but equally impressive in its engineering. Originally designed for large-scale coal mining in Germany, the Bagger 288 became world famous after completing one of the most extraordinary relocations ever attempted. Instead of dismantling the machine into thousands of individual components, engineers decided to move the entire 14,000-ton excavator across roads, rivers, railway lines, and farmland to its new mining location. The journey covered more than 20 kilometers and required weeks of careful planning. Temporary roads were constructed, utilities were relocated, and bridges were reinforced to support the machine's incredible weight. Thousands of people watched as one of the largest moving machines ever built slowly crossed the landscape at walking speed. Although bucket wheel excavators dominate surface mining, giant hydraulic excavators have become equally important in modern construction and mining projects. Machines such as the Caterpillar 6090 FS and the Komatsu PC 8000 weigh hundreds of tons and use enormous hydraulic cylinders capable of generating tremendous digging force. Unlike bucket wheel excavators, these machines offer greater flexibility, allowing operators to excavate different materials, load ultra-class mining trucks, and work in more confined environments. Their massive buckets can carry dozens of cubic meters of material in a single scoop, while powerful diesel-electric systems deliver the strength needed to excavate some of the hardest rock formations on Earth. Operating machines of this size requires extraordinary precision. Modern excavators rely on satellite positioning systems, laser guidance, onboard computers, and advanced monitoring software to maximize productivity while minimizing fuel consumption and mechanical wear. Sensors constantly measure hydraulic pressure, engine performance, structural loads, vibration, and component temperatures. Artificial intelligence is increasingly being used to optimize digging cycles, predict maintenance requirements, and improve operational efficiency. In many mining operations, operators no longer depend solely on visual observation. Instead, they work with digital terrain models displayed on large computer screens inside climate-controlled cabins, allowing every movement to be planned with remarkable accuracy. Maintaining these engineering giants is an enormous task in itself. Their crawler tracks, hydraulic systems, bucket teeth, conveyor belts, bearings, electric motors, and structural components operate under tremendous loads every hour of every day. Maintenance crews work continuously to inspect, lubricate, replace, and repair critical components before failures occur. Even replacing a single bucket tooth can require heavy lifting equipment and specialized crews because each component may weigh several hundred kilograms. Every hour of downtime represents significant financial loss, making preventive maintenance just as important as the machine's original design. Despite their astonishing size, these excavators represent only one category of the world's largest construction equipment. While they dominate mines by moving unimaginable quantities of earth, another group of engineering giants performs an entirely different mission beneath our feet. Deep underground, enormous tunnel boring machines carve their way through mountains, cities, and even beneath oceans, creating transportation networks that connect millions of people. In the next chapter, we'll step inside these incredible underground giants and discover how they excavate some of the longest and most complex tunnels ever built by humanity. While giant excavators dominate the surface, another class of construction machines operates in complete darkness deep beneath the ground. These machines are responsible for building the underground infrastructure that modern cities depend on every single day. From metro systems and railway tunnels to highway connections beneath mountains and massive underwater passages, none of these projects would be possible without one extraordinary invention: the tunnel boring machine, better known as the TBM. Unlike conventional excavation equipment, a TBM is not simply a machine that digs. It is a fully integrated underground factory capable of excavating rock, transporting debris, installing tunnel walls, injecting grout, monitoring geological conditions, and constructing a finished tunnel simultaneously. Some of the largest tunnel boring machines ever built measure more than 17 meters in diameter, stretch over 150 meters in length, and weigh more than 4,000 tons. Their size alone makes them among the most impressive construction machines ever created. At the front of every TBM is a gigantic rotating cutter head covered with dozens of heavy-duty steel disc cutters. As the cutter head slowly rotates, each cutter presses against solid rock with enormous force, breaking it apart through continuous pressure rather than explosive impact. Depending on the geological conditions, a TBM may advance only a few centimeters every minute. Although this seems slow, the machine works continuously 24 hours a day for months or even years, eventually excavating tunnels that stretch for dozens of kilometers. Every meter requires extraordinary precision because even the smallest deviation could create serious alignment problems later in the project. Immediately behind the cutter head lies a sophisticated system of hydraulic cylinders that push the entire machine forward. These cylinders do not push against the surrounding rock. Instead, they press against the concrete tunnel rings that the machine has already installed behind itself. As the cutter head advances, robotic manipulators lift massive precast concrete segments, weighing several tons each into position. 6 or 7 segments form a complete circular ring that becomes the permanent wall of the tunnel. High-strength bolts lock the segments together, while specially designed rubber gaskets create watertight seals capable of resisting enormous groundwater pressure. Once a ring has been completed, the hydraulic cylinders extend again, pushing the TBM forward to begin the next excavation cycle. This remarkable process repeats thousands of times until the tunnel reaches its final destination. Behind the segment installation area, another hidden engineering system is continuously at work. Specialized grout is injected into the gap between the surrounding rock and the newly installed tunnel lining. This fills every small void, stabilizes the ground, distributes structural loads, and prevents future settlement. Engineers carefully monitor the pressure and volume of every grout injection because uneven filling could affect the long-term stability of the tunnel. Although passengers will never see this hidden layer once construction is complete, it plays a critical role in ensuring the tunnel remains safe for more than a century. One of the most extraordinary engineering challenges is maintaining perfect alignment. Modern TBMs rely on laser guidance systems, gyroscopic navigation equipment, satellite survey data, and advanced onboard computers capable of measuring their position with millimeter accuracy. Every movement is continuously compared with the digital design model. If the machine begins drifting slightly off course, operators immediately make tiny corrections using hydraulic steering cylinders. This incredible precision becomes especially important when two TBMs begin excavating from opposite directions. After years of tunneling beneath mountains or oceans, both machines must meet almost perfectly at the center of the project. In some of the world's greatest tunneling achievements, the final alignment error has been measured in only a few centimeters after excavating more than 20 kilometers. Modern TBMs are also becoming increasingly intelligent. Hundreds of sensors constantly monitor cutter wear, hydraulic pressure, motor temperature, vibration, ground conditions, electrical systems, and machine performance. Artificial intelligence analyzes this information in real time, helping engineers predict maintenance requirements before failures occur. Instead of replacing components only after they break, operators can now schedule maintenance during planned construction stops, significantly reducing delays while extending machine life. Some of the newest TBMs can automatically adjust cutter head speed, hydraulic pressure, and excavation force depending on the hardness of the surrounding rock, maximizing both productivity and safety. Working inside one of these underground giants is unlike any other construction environment. Teams of engineers, electricians, mechanics, surveyors, and machine operators work around the clock inside narrow underground spaces surrounded by hundreds of tons of moving equipment. Ventilation systems continuously supply fresh air while removing dust and heat generated by excavation. Conveyor belts transport thousands of tons of broken rock toward the tunnel entrance, where it is loaded onto trucks or trains for removal. Every operation follows strict safety procedures because a mechanical failure or unexpected geological condition deep underground can quickly become extremely dangerous. The impact of these incredible machines extends far beyond tunnel construction. Without TBMs, many of today's most ambitious infrastructure projects would simply be impossible. High-speed railway systems crossing mountain ranges, metro networks beneath crowded cities, underwater tunnels connecting entire countries, and utility tunnels carrying water, electricity, and communications all depend on these engineering giants. Every kilometer excavated beneath the earth represents thousands of hours of precision engineering performed by machines operating in one of the harshest environments imaginable. Yet even tunnel boring machines are not the largest lifting or construction equipment ever built. When engineers need to assemble offshore platforms, install bridge sections weighing thousands of tons, or build skyscrapers reaching into the clouds, they rely on another family of engineering giants. These machines do not dig beneath the earth. Instead, they lift impossible loads high into the sky. In the next chapter, we'll explore the world's largest cranes and discover how these incredible machines make modern megaprojects possible. While excavators remove mountains and tunnel boring machines carve paths beneath the earth, another family of engineering giants performs an equally extraordinary task. They lift loads so enormous that no other machine on Earth could move them. Modern megaprojects would be impossible without giant cranes capable of placing bridge sections weighing thousands of tons, assembling offshore oil platforms larger than football fields, installing wind turbines taller than skyscrapers, and constructing buildings that rise hundreds of meters into the sky. Every time we see a completed suspension bridge, a massive power plant, or an offshore platform standing in the middle of the ocean, there is one machine working quietly behind the scenes that made it all possible. These are the world's largest cranes, and they represent some of the most powerful lifting machines ever created by humanity. Among them, few are more impressive than the legendary Liebherr LR 13000. Recognized as one of the most powerful conventional crawler cranes in the world, The LR13000 is capable of lifting an astonishing 3,000 tons. To understand the scale of that achievement, imagine lifting hundreds of fully loaded trucks into the air at the same time. Standing more than 200 meters tall when fully configured, the crane dominates every construction site where it operates. Its enormous lattice boom reaches into the sky, while massive crawler tracks distribute thousands of tons of weight across the ground, allowing the machine to move slowly while carrying incredible loads. Yet despite its enormous size, every movement is controlled with astonishing precision, often measured in just a few millimeters. Building and transporting a crane of this scale is itself a massive engineering project. Unlike ordinary construction equipment that arrives on a single trailer, giant crawler cranes are delivered in hundreds of separate components. Steel boom sections, crawler assemblies, counterweights, winches, hydraulic systems, engines, and control cabins are transported individually before being assembled on site. In some cases, assembling the crane requires several weeks of work and the assistance of smaller cranes. Thousands of tons of counterweights must be carefully installed behind the main boom to balance the enormous loads lifted at the front. Every calculation is critical because even a slight imbalance could affect stability during operation. Engineers use sophisticated computer software to determine exactly how much counterweight is required for every lifting operation, taking into account boom length, wind speed, ground conditions, lifting radius, and the weight of the load itself. Offshore construction presents an even greater challenge. Installing oil platforms, offshore wind turbines, and subsea infrastructure requires cranes capable of operating from floating vessels in constantly changing sea conditions. One of the most remarkable examples is Sleipnir, one of the world's largest crane vessels. Equipped with two gigantic revolving cranes, each capable of lifting 10,000 tons, Sleipnir can install some of the heaviest offshore structures ever built. Massive platform modules, jackets, subsea equipment, and wind turbine foundations weighing thousands of tons are lifted from transport barges and positioned with extraordinary accuracy despite waves, wind, and ocean currents. Dynamic positioning systems controlled by satellite navigation continuously adjust the vessel's position using multiple powerful thrusters, allowing operators to perform lifts that would have been considered impossible only a few decades ago. Bridge construction also relies heavily on giant lifting equipment. Modern suspension bridges and cable-stayed bridges are assembled piece by piece, often hundreds of meters above rivers or valleys. Steel bridge segments weighing hundreds or even thousands of tons must be lifted into position with extreme precision before being permanently connected. During these operations, crane operators work closely with engineers, surveyors, and rigging specialists to ensure every component aligns perfectly. Strong winds, changing temperatures, and even slight structural movement caused by the weight of the bridge itself must all be considered before each lift begins. A single operation may take several hours, yet every movement is measured in centimeters. Modern cranes are no longer controlled by mechanical levers alone. Advanced onboard computers continuously monitor load weight, boom angle, wind speed, ground pressure, hydraulic pressure, and structural stress. If any operating limit is approached, the computer immediately warns the operator or automatically prevents dangerous movements. Multiple sensors constantly verify that the crane remains within its safe operating envelope. Artificial intelligence is beginning to assist operators by analyzing lifting plans, predicting equipment wear, and optimizing lifting sequences for maximum efficiency and safety. Some heavy lifting operations now use digital twin technology to simulate every stage of the lift before it takes place in the real world, allowing engineers to identify potential risks long before the first component leaves the ground. Despite their incredible capabilities, giant cranes face enormous challenges every day. Wind remains one of the greatest dangers during heavy lifting operations. Even a moderate gust can create massive forces on large steel structures suspended high above the ground. Operators constantly monitor weather conditions and immediately suspend operations if wind speeds exceed safe limits. Ground stability is equally important. Before a crane begins lifting, engineers carefully analyze soil conditions to ensure the ground can safely support thousands of tons concentrated beneath the crawler tracks or outriggers. Temporary steel mats, reinforced foundations, and specially prepared working platforms are often required before heavy lifting operations can begin. The world's largest cranes demonstrate that lifting enormous loads is not simply a matter of brute strength. It is a combination of structural engineering, advanced materials, sophisticated computer systems, precise planning, and highly skilled operators working together with extraordinary coordination. These engineering giants quietly perform some of the most demanding tasks in modern construction, making possible projects that once existed only on architects' drawings. Yet even these incredible machines are now entering a new era. Artificial intelligence, autonomous operation, electric power systems, and fully connected construction sites are beginning to transform the future of heavy equipment. In the next chapter, we'll explore how technology is creating a new generation of intelligent construction machines capable of building tomorrow's megaprojects faster, safer, and more efficiently than ever before. The world's largest construction machines are already capable of accomplishing tasks that once seemed impossible. They move mountains, excavate tunnels beneath oceans, lift thousands of tons into the sky, and help build some of the most ambitious megaprojects in history. Yet despite their incredible capabilities, engineers believe today's machines represent only the beginning. A new technological revolution is transforming the construction industry, driven by artificial intelligence, robotics, automation, satellite positioning, and digital engineering. The machines of tomorrow will not simply be larger or more powerful. They will become smarter, more efficient, safer, and increasingly capable of operating with minimal human intervention. Construction sites around the world are already beginning to resemble advanced technology laboratories rather than traditional work zones. Artificial intelligence is becoming one of the most important tools in modern heavy equipment. Today's construction machines are equipped with hundreds of sensors, continuously monitoring engine performance, hydraulic pressure, fuel consumption, structural loads, vibration, oil temperature, electrical systems, and countless other operating conditions. Every second, enormous amounts of information are transmitted to onboard computers and cloud-based monitoring systems. AI analyzes this data in real time, identifying patterns that would be impossible for human operators to detect. A slight increase in hydraulic pressure may indicate a worn cylinder seal. Tiny changes in vibration can reveal bearing damage long before mechanical failure occurs. Instead of repairing machines after they break down, construction companies can now schedule maintenance before problems become serious, dramatically reducing downtime while extending equipment life. Automation is also changing the way construction sites operate. Modern bulldozers, graders, and excavators increasingly rely on satellite navigation systems capable of positioning heavy equipment with centimeter-level accuracy. GPS receivers, laser guidance systems, and three-dimensional digital terrain models allow machines to automatically maintain the correct excavation depth, grading angle, and construction alignment without relying entirely on operator experience. Earth-moving operations that once required repeated manual surveying can now be completed with extraordinary precision on the first attempt. This not only improves efficiency, but also reduces material waste, fuel consumption, and construction costs. Some mining operations have already taken automation even further. In several of the world's largest open-pit mines, enormous haul trucks weighing hundreds of tons operate completely without drivers. Guided by artificial intelligence, radar and STADAR, GPS, and onboard cameras, these autonomous vehicles transport thousands of tons of material every day while communicating continuously with central control systems. They automatically adjust speed, avoid obstacles, coordinate with other equipment, and optimize transport routes without human intervention. Engineers believe similar autonomous technology will soon become common on major construction projects around the world. Electrification is another major trend reshaping heavy equipment. Traditionally, the world's largest construction machines have depended on enormous diesel engines to generate the power needed for excavation, lifting, and transportation. However, growing environmental concerns and advances in battery technology are encouraging manufacturers to develop electric excavators, electric cranes, hybrid loaders, and zero-emission construction equipment. Although fully electric machines currently operate mainly in smaller applications, larger battery systems, hydrogen fuel cells, and advanced electrical power networks may eventually transform even the biggest construction machines. Quieter operation, lower emissions, reduced maintenance, and improved energy efficiency are becoming increasingly important for construction projects located near cities and environmentally sensitive areas. Remote operation is also expanding rapidly. Instead of sitting inside dangerous construction environments, operators can now control certain machines from safe locations using high-definition cameras, real-time sensors, and advanced communication networks. In hazardous environments such as unstable mines, disaster zones, radioactive facilities, or deep underground excavation sites, remote-controlled equipment significantly improves worker safety while maintaining productivity. As communication technology continues improving, experts believe that future construction projects may be managed from centralized control centers located hundreds or even thousands of kilometers away from the actual job site. Digital twin technology is transforming project management as well. Every major construction machine can now have a complete virtual replica existing inside powerful engineering software. These digital models receive continuous information from the real machine, allowing engineers to monitor performance, simulate future operating conditions, predict component wear, and optimize maintenance schedules before problems occur. Entire construction sites can be recreated digitally, enabling project managers to coordinate hundreds of machines with unprecedented efficiency while reducing delays and avoiding costly conflicts between different phases of construction. Perhaps the most exciting development is the integration of multiple intelligent systems into a single connected construction site. Excavators communicate with dump trucks. Cranes receive lifting instructions directly from digital building models. Survey drones continuously update terrain maps. AI coordinates machine movements to maximize productivity while reducing fuel consumption and idle time. Every machine becomes part of one enormous digital ecosystem working together toward the same objective. Instead of individual operators making isolated decisions, future construction sites will function as highly coordinated, intelligent networks capable of adapting automatically to changing conditions. Although these technologies sound futuristic, many of them are already being used on some of the world's largest infrastructure projects. Engineers are not replacing human expertise. Instead, they are giving construction professionals better tools to solve increasingly complex engineering challenges. As megaprojects continue growing larger, deeper, taller, and more ambitious, the machines building them must evolve as well. The next generation of construction giants will combine immense mechanical power with advanced artificial intelligence, allowing humanity to build faster, safer, and more efficiently than ever before. In our final chapter, we'll discover how these extraordinary machines have changed civilization itself and why they remain the hidden heroes behind every great engineering achievement on Earth. As we reach the end of our journey, one thing becomes unmistakably clear. The world's greatest construction machines are far more than giant pieces of steel and hydraulic equipment. They are the silent forces that have shaped modern civilization. Every highway stretching across mountains, every tunnel carved beneath the sea, every record-breaking skyscraper, every massive hydroelectric dam, every international airport, and every futuristic city begins with these engineering giants. Before architects can admire their finished designs, and before millions of people benefit from new infrastructure, these extraordinary machines must first perform the impossible. They move mountains, excavate solid rock, lift thousands of tons with astonishing precision, and create the foundations upon which modern society is built. Without them, many of humanity's greatest engineering achievements would never have existed. What makes these machines truly remarkable is not only their incredible size, but also the engineering knowledge behind them. Every component has been designed to withstand extreme conditions. Massive hydraulic cylinders generate forces powerful enough to move entire buildings. Steel structures carry loads measured in thousands of tons, while maintaining millimeter-level precision. Sophisticated computer systems constantly monitor vibration, temperature, pressure, and structural stress to ensure safe operation every second of every day. Behind every giant excavator, tunnel boring machine, crawler crane, or mining truck stand thousands of engineers, designers, technicians, manufacturers, and operators whose combined expertise transforms ambitious ideas into working reality. These machines are living demonstrations of what engineering can achieve when innovation meets determination. Perhaps the greatest achievement of modern construction equipment is the way it has expanded the limits of human imagination. Projects that once seemed impossible have become routine. Mountains that once divided countries are crossed through tunnels stretching for dozens of kilometers. Oceans that separated nations are connected by bridges and underwater tunnels. Cities continue reaching higher into the sky, while offshore wind farms rise far beyond the horizon. Every generation of construction machines has allowed engineers to dream even bigger than the generation before. As machinery became stronger, more precise, and more intelligent, the scale of human ambition expanded with it. Today's megaprojects would have been unimaginable only a few decades ago, yet they are becoming increasingly common around the world. The future promises even greater transformation. Artificial intelligence is allowing machines to monitor their own performance and predict maintenance before failures occur. Autonomous construction equipment is already operating on mining sites and major infrastructure projects. Digital twins enable engineers to simulate entire construction processes before work begins. Electric and hydrogen-powered heavy equipment is reducing emissions while maintaining extraordinary performance. Advanced robotics, satellite positioning, drone surveying, and fully connected construction sites are creating a future where giant machines operate with levels of precision and efficiency never before possible. The next generation of engineering giants will not only be stronger, but also smarter, safer, and more sustainable than anything humanity has built so far. Yet despite all this technological progress, one thing remains unchanged. Machines do not replace engineers, they extend human capability. Every remarkable construction project still begins with an idea, a drawing, a calculation, and the determination to solve problems that appear impossible. Construction machines are simply the tools that allow those ideas to become reality. Behind every rotating cutter head, every towering crane, every giant excavator, and every powerful hydraulic system is human creativity pushing the boundaries of what can be achieved. Throughout history, civilization has always advanced because people refuse to accept existing limitations. These engineering giants are physical proof of that relentless pursuit of progress. The world's biggest construction machines remind us that true engineering is not measured only by the size of the equipment or the height of a building. It is measured by the problems solved, the lives improved, and the opportunities created for future generations. Every road that shortens a journey, every tunnel that connects communities, every bridge that spans an impossible gap, and every city that continues to grow is the result of countless hours of engineering excellence supported by these incredible machines. They rarely become famous. Most people never know their names. Yet they remain the hidden heroes behind nearly every great construction achievement on Earth. As humanity prepares to build smarter cities, longer tunnels, taller skyscrapers, cleaner energy systems, and even infrastructure on the Moon and Mars, one thing is certain. The machines of tomorrow will once again redefine what is possible. They will become larger, more intelligent, and more capable than anything we see today. But they will continue serving the same purpose they have always served, to transform impossible ideas into reality. Thank you for watching Hills BuildVerse. If you enjoy exploring the world's greatest megaprojects, giant construction machines, groundbreaking engineering, and the technologies shaping the future of civilization, be sure to subscribe and join us on our next adventure. Because somewhere in the world, another engineering giant is already at work, building the future one incredible project at a time.